Hey Jordan, you got a minute? I was just looking at this paper, querying labeled time series data with scenario programs, and it seems pretty interesting.
Oh yeah? What's the gist? The title sounds a little dense.
It is, but the core idea is actually super cool. We're looking at a new way to search through massive amounts of data, specifically labeled time series data. Think about all the video footage self-driving cars collect.
Okay, so we're talking about finding stuff in those videos, like find all clips with a pedestrian crossing the street?
Exactly, but way more specific and complex. It's about using a special programming language called Scenic to write a formal definition of a whole scenario. So instead of just a pedestrian, you could describe something like, a car is following the lane, but then a second car is stalled ahead, so the first car has to make a sudden lane change to avoid it, but only if the distance is less than 15 meters.
Ah, so you're not just searching for objects, you're searching for a whole story, a sequence of behaviors and interactions. You write that story in Scenic, and this thing goes and finds it in real-world driving data.
You got it. That's the main topic. Using a formal program as a search query.
That makes sense. But why is that such a big deal? What's the problem they're trying to solve?
Well, it all comes down to this thing they call the sim-to-real validation problem. Researchers are great at finding bugs and failure scenarios for autonomous vehicles inside a simulation. They can run millions of tests and find these really specific edge cases where the AI messes up.
Right. I've seen that. The simulator finds a weird situation where the car turns into a wall or something.
Exactly. But here's the catch. Is that scenario just an artifact of the simulation? Is it something that could even happen in the real world? Or is it a genuine, critical bug that needs to be fixed? It's really hard to know.
So the problem is bridging that gap. You find a failure in the fake world, but you need to know if it's a real danger in the real world. And to do that, you'd have to find instances of it happening.
Precisely. And right now, there's no good way to do that at scale. You could try using standard database queries, but they're way too simple. They can find a car and a pedestrian, but they can't understand the complex temporal behavior. Like, the car yields to the pedestrian only after braking hard.
Okay, so simple database queries are out. What about the new stuff, like asking an AI? Couldn't you just describe the scenario in plain English to a vision language model? AVLM, like GPT-4o?
They actually talk about that. It's one of their main comparison points. The problem with natural language is that it's often ambiguous. What does gets too close mean? How fast is suddenly? The VLMs can get confused, they hallucinate, and they're often just plain wrong. There are no guarantees on accuracy.
So you're stuck between a rock and a hard place. One method is too simple to describe what you want, and the other is too ambiguous and unreliable to find it correctly.
That's the problem in a nutshell. There isn't a scalable, precise, and expressive way to search massive real-world datasets for these complex event sequences.
And that's where their solution comes in, the formal query algorithm. How does it actually work?
So the first step is what we talked about. A developer or safety engineer writes a very precise description of the scenario they're looking for using the Scenic language. This isn't English, it's code, so there's no ambiguity.
Okay, so you have this formal Scenic program. What's next? You can't just feed a program into a video file.
Right. This is the clever part. The algorithm takes that Scenic program and translates it into a set of what they call hierarchical finite state machines, or HFSMs.
Whoa, that's a mouthful. What is an HFSM in simple terms?
Think of it like a very detailed flowchart or a formal recipe for behavior. For each object in the scenario, like ego car or other car, it creates a state machine that says exactly what it can and can't do at any given moment. For example, the ego car, HFSM, might have a follow lane state. There'd be a transition out of that state to a change lane state. But the transition is only allowed if a specific condition is met, like distance to car in front is less than 15 meters.
So it's a formal model of all the possible correct behaviors for each object, according to the scenario you wrote. It's like a rule book.
A perfect way to put it. It's a formal rulebook for every actor in the scene. Once it has these rulebooks, the algorithm starts looking through the labeled time series data. Data already has objects tagged, with their positions, speeds, what lane they're in, etc.
And how does it do the actual searching?
It uses a sliding window approach. It looks at a chunk of the video data at a time, say 5 seconds long. And for that chunk, it performs two critical checks. First is the correspondence search.
What's that?
Well, your Scenic program has abstract objects named ego car and stalled car. The video data has real objects named car 1, car 27, car 54. The algorithm has to figure out which real car could be the ego car and which could be the stalled car.
Oh, I see. It has to find a plausible mapping, like it's not going to map your stalled car to a car that's moving at 60 miles per hour. It has to match the characters from your script to the actors on the screen.
Exactly. It creates a hypothesis, like, let's assume car 27 is our ego car, and car 54 is our stalled car. Once it has a correspondence, it moves to the second check, the behavior match.
This must be where those HFSM rulebooks come back into play.
Yep, it now replays the events from that 5-second window of data and checks if the actions of car 27 and car 54 strictly follow the rules laid out in their respective HFSMs. It goes step by step by time step through the data. At each point it asks, given what's happening in the world right now, is the behavior I'm seeing in the data a valid move according to the state machine?
So if car 27 changes lanes, but the conditions for a lane change in the rulebook aren't met, then the match fails.
The match fails. And the algorithm concludes that this 5-second window, with this specific object correspondence, is not an instance of the scenario. It then either tries a different correspondence, maybe car 12 was the ego car, or it slides the window forward and starts over on the next chunk of video.
That's a really methodical process. It sounds slow, but I guess it has to be accurate. So, did they test this? How did it actually perform?
This is the wild part. They tested their algorithm against those state-of-the-art VLMs you mentioned, specifically GPT-4o and CLAUDE 3.5, on both accuracy and speed.
Okay, I'm ready. How did it do?
It crushed them. In terms of accuracy, their algorithm averaged 80% across the test scenarios.
80% is pretty good. How'd GPT-4o do?
60%. And Claude was even lower, around 45%. So it's significantly more accurate.
Wait, really? So almost half the time, the big fancy API models were just wrong about whether the scenario was in the video? That's, not great for them.
Not at all. But the speed difference is even more staggering. Their algorithm took, on average, 0.06 seconds to query a video.
0.06 seconds? That's practically instant.
Right? Now guess how long GPT-4o took for the same query?
I don't know, maybe a few seconds? 5, 10 seconds?
Over 41 seconds.
No way. 41 seconds versus 0.06? That's not just faster, that's a completely different class of performance. That's orders of magnitude. Who could run hundreds of their queries in the time it takes GPT to run one?
It's a total blowout. It proves that for this specific, formal task, a specialized algorithm is just vastly superior to a general-purpose model.
Okay, so it's accurate and lightning fast. What about scalability? You can't just test it on 5-second clips. What if you have an hour of video or a really complicated scenario with tons of cars?
Great questions. They looked at that too. For the length of the data, it scales beautifully. The runtime increases linearly. So if you double the length of the video, the search time roughly doubles. That's very manageable.
That's the good news. I'm sensing there's bad news.
There is. It does not scale well with the number of objects in the query. The runtime grows exponentially.
Why is that?
It goes back to that correspondence search step. If your scenario has 2 cars, and there are 10 cars in the video clip, there are a bunch of possible mappings to check. But if your scenario has 8 cars, the number of possible ways to map those 8 scenario objects to the real cars in the video just explodes. It's a combinatorial nightmare. They showed a graph where the runtime shoots up to the sky once you get past 6 or so objects.
So it's great for simple, focused scenarios with a few key actors, but you couldn't use it to find a complex 10-car traffic jam interaction. At least not yet.
Exactly. That's the main limitation they identified.
Makes sense. So, to wrap it all up, what's the final verdict?
In conclusion, the paper presents a really powerful new method. It's a formal, provably correct way to query labeled sensor data for these really specific, complex scenarios.
And this method is way more accurate and astronomically faster than just asking a big language model to watch the video for you. It feels like a massive step forward for that whole sim-to-real validation problem we started with.
Totally. It gives engineers a practical tool to take those weird failure cases from a simulation and actually go find them in petabytes of real-world data to see if they're a real threat.
but with the big caveat that it works best for scenarios with a limited number of objects. Improving that combinatorial correspondence search is probably their next big research project.
I would bet on it. Still, it's a huge step in the right direction.
For sure. Thanks for breaking that down. That was super clear.
No problem. It was a cool paper.
Catch you later.
Later.